Friends, so far we have studied the analysis of the continuous beams without settlement and sinking of the support. Today we will discuss about the analysis of the continuous beams with the sinking of the support by using the stiffness matrix method. Here the problem is analyze the continuous beam shown in figure by direct stiffness method. If support B, one of the support B yields by 9 millimeter, we have to consider the sinking of the support in the analysis, that is one of the support B that settles by 9 millimeter. Take the value of the flexural rigidity EI equals 1 into 10 to the power of 12 Newton millimeter square throughout. Here A is the fixed end, A to B 3 meter at a distance of 2 meter from A, 1 meter from B is subjected to a load of 60 kilonewton and support B is on roller. B to C, the length is 6 meter and is subjected to UDL of 20 kilonewton per running meter. C is on roller and a small portion of the beam is extended beyond the support over a length of 1 meter up to D from C and is subjected to a point load of 20 kilonewton in downward direction as shown in figure. Here he has not given any variation of the flexural rigidity from A to D, hence we have to consider the flexural rigidity EI is constant. First we have to calculate the degree of freedom to consider the redundance. Here the degree of freedom at the fixed end A is 0. At B the degree of freedom is, here it is free to rotate or it allows the rotation of the end of the beam, that is theta B. Here the end A is fixed rigidly, hence there is no movement in the direction of the roller support, hence theta B is the only one unknown at B, only 1 degree of freedom at B. Similarly at C also there is only 1 degree of freedom, that is theta C, hence the total degree of freedom 0 plus 1 plus 1, that is 2, that is theta B and theta C are the redundants we have to consider. Then the second step is to calculate the fixed end moment. Here we have to consider the fixed end moments due to the loads applied, as well as we have to calculate the additional fixed end moment due to the sinking and settlement of the support. Here first we have to consider span AB. AB is subjected to a point load of 60 kilonewton at a distance of A equals 2 meter, B equals 1 meter. The total length is A plus B, that is 3 meter. That is MF AB is anti-clockwise, hence that is minus W is AB square by L square minus 60 into 2 into 1 square divided by 3 square. By substituting the values, you will get the value of minus 13.33 kilonewton meter. Similarly, from the other end, MFBA, that is WA square B by L square, WA is 60, A square, that is 2 square, B 1 meter divided by L square, that is 3 square. By simplification, you will get a value of 26.67 kilonewton meter. Then MFBC, it is subjected to UDL of 20 kilonewton per meter over a length of 6 meter. Then from B, the fixed end moment is anticlockwise, that is WL square by 12, W is 20, L is 6. Hence, by substituting the values, that is minus 20 into 6 square by 12, that equals minus 60 kilonewton meter. Then from the other end, MFCB, that is clockwise, that is positive, MFCB equals plus 60 kilonewton meter, that is WL square by 12. By substituting the values, you will get a value of fixed end moment as 60 kilonewton meter due to load. Here there is a small portion is extended beyond the support, that is overhang, that we will consider later. Here Then after knowing the values of the fixed end moment due to the load, now we have to calculate the additional fixed end moments due to the sinking and settlement of the support. Here in this current problem, the support B sinks by an amount of 9 millimeter in downward direction as shown in figure. Here with the relative moment of B with respect to A, that is the rotation is in clockwise direction. Here the settlement is 9 millimeter in downward direction. Hence delta for span, the settlement for the span AB is 9 millimeter since the rotation is clockwise, that is positive, that is 9 millimeter, that equals 0.009 meters. If you convert that to meters, it is 0.009 meters. Similarly, the relative motion between the B and C, with respect to C, the rotation is in anti-clockwise direction. Hence, this settlement in portion BC is negative, that is delta equals minus 9 millimeter for span BC, that is minus 0.009. Then to calculate the additional fixed end moment due to the settlement and sinking of the support, here he has given the value of EI as 1 into 10 to the power of 12 Newton millimeter square. We have to convert this into kilonewton meter square. Newton is converted to kilonewton, that is divided by 1000. Millimeter is divided into meters divided by 1000. Here the millimeter square, hence Newton millimeter square can be converted to kilonewton meter square by dividing 1000 cube. You will get the value of 1000 kilonewton meter square. Now the additional fixed end moment. Here C to D it remains same, there is no effect of settlement. Then M dash F AB, that is additional fixed end moment, is given by minus 6 EI delta by L square. Here for span AB, M dash AB, that is settlement is plus 0.009 meter. The formula is minus 6 EI delta by L square minus 6, EI value is 1000, delta is plus 0.009 divided by L square, that is minus 6 kilonewton meter. Similarly, M dash FBA from the other end also, that is same, that is minus 6 kilonewton meter. Then M dash FBC, with respect to B, with respect to C, there is a relative moment in anti-clockwise direction. Hence delta B is delta in portion BC is negative, that is minus 0.009. By substituting the values, that is M dash FBC, that equals minus 6 EI delta by L square minus 6, EI value is 1000, delta is minus 0.009 divided by length is 6. Then by substituting the values minus into minus plus, then that becomes 1.5 kilonewton meter. Similarly from the other end, that is M dash FCB, that one is again 1.5 kilonewton meter. Now we have to get the vector of the load at coordinates 1 and 2. This one is, here we have considered theta B as the redundant, theta C as one of the redundant. We have to give the name, the coordinates numbers, that is 1 and 2. Here first we have to get the net fixed end moment due to load as well as the settlement. Here MFAB, net fixed end moment is 13.33 minus 6, that is minus 19.33 at from A to B. From B to A, that is 26.67 minus 6, that is 20.67 kilonewton meter. In span BC, MFBC, that is net fixed end moment, that is minus 60 plus 1.5, that is minus 58.5 kilonewton meter. From C to B, that is plus 60 plus 1.5, that is 61.5 kilonewton meter. Now we will get the vector due to the load acting at the coordinates, that is due to the fixed end moment due to the load, fixed end moment due to the settlement of the support. Here at coordinate 1, two spans are connected, one is BA, one is BC. Hence we have to add both the moments at MFBA and MFBC. That is MFBA is just now we have calculated, that is net value, that is 20.67. Net value of the fixed end moment in span BC, that is minus 58.5. That is P1L equals 20.67 minus 58.5, that is minus 37.83. Similarly at coordinate 2, here there is MFCB. MFCB is just now we have calculated, that is the net fixed end moment, that one is 61.50, then P2L equals 61.50. Here this is the vector due to the load at coordinates 1 and 2 respectively. Then to find the load due to find the vector due to loads, if any acting on the end supports, that is due to the overhanged portions. Here C to D is overhanged. Then at coordinate 2, the vector due to the load is given by P equals, at 1 there is no such loads, pre-existing loads, then this is 0. Here at 2, due to this moment due to this overhanged portion, the actual moment is 20 into 1, that is clockwise, hence that is positive. Then we have to write, that is P2 equals 20 at coordinate 2. Then the vector due to P is given by P1, P2, 0 at P1, at 2, that is 20. Then we have to calculate the stiffness matrix. Stiffness matrix by applying the unit rotations at coordinates 1 and 2 separately. First we have to apply the unit rotation at 1 as shown in figure. Here the unit rotation is in clockwise direction. Here K11, that is stiffness element, that is K11. Here we have applied the unit rotation at 1. Due to this unit rotation, the stiffness value at 1 due to load applied, rotation applied at 1, that is K11. K11 equals, here there are two spans, one is B to A, one is B to C. Hence we have to consider both the spans. Due to that, here it will undergo deformation like this. Here this is the deformation due to the unit rotation applied at coordinate 1. Here the angular displacement at 1 due to the unit rotation applied at 1, that is in span BA, that is 4EI by L, or by slope deflection equation, 2EI inside of the 2EI by L inside of the bracket 2 theta. You can use that equation, or directly 4EI by L for span BA, 4EI by L for span BC. Here 4EI by length of the span BA is 3 meter, that is 4EI by 3 for span BA. For span BC 2EI, that is 4EI by 6, directly we can write. Then after simplification, that is 2EI. Then at 2, the unit rotation applied is at 1, the stiffness value at 2 due to the unit rotation applied at 1, that is K21. That one is, here this is the far end from 1, hence that is 2EI by the length of this span, that is 2EI by 6, that is after simplification 1/3 of EI. Now after getting the stiffness values at 1 and 2, now we can apply the unit rotation in for the coordinate 2 due to the application of the unit rotation. due to the unit rotation here at 2, it will undergo deformation. This is the stiffness value at 2 due to the unit rotation applied at 2 in clockwise direction. Then K22 equals, that is, this is the near end, or by using the slope deflection equation for near end, it is 4EI by L. L is 6, that is 4 by 6, that is 2/3 of EI. Similarly, for the stiffness value at 1 due to the unit rotation applied at 2, that one is here 2EI by L, that is 2EI by 6, 1/3 of EI. Here, by observing the values of K12 and K21, both must be equal, that is by the Maxwell's reciprocal theorem. Now, we can write the stiffness matrix for this one as here. This one is the stiffness matrix, that is K equals EI is common in all the elements, hence we have to write the stiffness value by taking K common, that is outside. The first element in first row, first column, that is 2. Second column, that is second element of the first row, that is 1/3. First element of the second column, that is second row, that is 1/3. Second element of the second row, that is 2/3. Here, this is the stiffness matrix for the given problem. We know that to find the redundance, we know the equation, that is stiffness matrix into the displacement vector, that one equals the vector due to the load, pre-existing load, minus the vector due to the applied loads. Then here, by using this equation, we have to substitute the values. Here K is already we have calculated, we have written the stiffness matrix. Then the displacements, that is redundance matrix, that is theta B and theta C are the redundance. Then we have just now we have calculated P1 is 0, P2 is 20, that is due to the overhanged portion. Then the net moment at B or coordinate 1, that is minus 37.83, minus into minus, this becomes plus. And P2L, that is 61.50, that is positive, that is minus 61.50. Here, after simplification, we will get the values of theta B as 31.95 by EI, theta C as 78.23 by EI. Now, after knowing the values of the redundance, we can substitute the values of the redundance in slope deflection equation, that is MAB. MFAB, that is net moment, net fixed end moment due to both the load as well as the settlement of the support. Hence, MFAB is minus 19.33 plus 2EI by L. L is 3. The flexural rigidity EI is 1 EI. Then inside of the bracket 2 theta A. Theta A is 0 since the end is fixed, plus far end 1 theta B. Theta 1B is, that is 31.95 by EI, minus 3 delta by L. That is, don't consider that, since we have already considered the moment due to the settlement of the support. This is the net fixed end moment. Hence, don't write minus 3 EI delta 3 delta by L. That one is, after simplification, 1.97 kilonewton meter. MBA, that one is the net fixed end moment due to both load as well as the settlement of the support, that is 20.67 plus 2EI by L. L is 3. Inside of the bracket, theta A, 1 times theta A, that is far end, theta A is 0, plus 2 times the near end, that is theta B, 2 into 31.95 by EI. Here we will get, after simplification, 63.27 kilonewton meter. Here, by observing both MAB and MBA, both are clockwise, then MBC, that is MF BC due to the load as well as the settlement of the support, that is minus 58.50 plus 2 EI by L, the length is 6 meter, inside of the bracket 2 theta B is the near end, that is 2 into 31.95 by EI, plus theta C, that is the far end, 1 times theta C, that is minus 78.23 by EI. After simplification, you will get minus 63.27 kilonewton meter. We know that at joint B, summation of MB must be equal to 0, that is MBA plus MBC must be both are same, or the summation must be equal to 0. One is positive, one is negative. Then MCB, that is at overhanged portion, already we have calculated the actual moment is 20 kilonewton meter. In span C to D, the resisting moment is minus 20 kilonewton meter for portion CD. For portion CB, MCB, that is the fixed end moment due to the load and the settlement, that is 61.50 plus 2 EI by L, well is 6 meter, inside of the bracket 2 theta C, that is 2 into minus 78.23 by EI, plus 1 times theta B, that is 31.95 by EI, that equals 20. Here this one is clockwise. By using these values, we can draw the bending moment diagram and shear force diagram. Afterwards, we can easily draw the elastic curve. Okay, we'll continue in the next video.